In this video, we're going to discuss the topic of integration. Now, before we actually talk about indefinite integrals, let's see what the integration process is. So one way to think of integration is the process of undoing the differentiation. So what I have here is that integration is opposite of differentiation. And what do we mean by that is informally I can think of differentiation as the process of taking a function apart, okay? And when we want to put the function back together the way it was, that process has to be done through integration. So integration puts it back together as a whole, while differentiation will kind of takes it apart. And I have a schematic of this. Suppose I have a function f of x, and usually what we've done up to this point is we found the derivative of the function, right, the slope of a tangent at every point. And if that's differentiation, then the process of going back now from f prime x to little f of x is called anti-differentiation or integration. And I have here the definition of antiderivative of f of x. So the antiderivative of a function of f of x is capital F of x. And what we mean by that is if you take the derivative of the antiderivative, remember in my schematic, the antiderivative here is the original function, which we labeled little f of x. But in the book and most every textbooks, they call that capital F of x, okay? So what that means is that if you take the derivative of this antiderivative, you get f of x, and for all x inside of an interval. So I have an example here. So I want to show that capital F of x, x to the fourth minus 7, is an antiderivative of f of x, which is 4x cubed. So what I'm going to do is take the derivative of that, and I have here, and the derivative turns out to be 4x cubed, right? That's the derivative here. And that is what the derivative is. There you go. So capital F is the antiderivative, okay? Little f here is the derivative. And I know we use f prime, but in this notation we call the derivative a function f of x. Now if you note here, I also have another function, the second function, capital F sub 2 of x. This is a second antiderivative, a different antiderivative of the function, right? But look at the similarity between f sub 2 and the f of x, which I can call it f sub 1. Now they have two of them. So if you look at the difference between those two antiderivatives, they're almost on the function side, on the variable side, they're exactly the same. It's just the constants are different, right? And of course, that's because the derivative of a constant is 0. So we actually have a theorem here. A theorem that reads, if capital F is an antiderivative of little f on an interval, then every antiderivative of f, little f, is of the form capital G of x equals f of x plus c. So what this theorem is telling me in a way is that we have a family of antiderivatives. And all of these antiderivatives have the same structure again on the independent variable side. It's just they're different by a constant. Okay, so now this process of trying to find the antiderivative of the function, of course, is called antidifferentiation or integration. So I'm just gonna write that differentiation is aka also known as integration. So that's what that is. So it's the process of finding the antiderivatives. Okay, now we need a notation, okay, an expression for that capital G of x. Okay, that capital G of x here, using this notation that your book uses, is written as the integral symbol of f of x and then dx. Okay, that's the meaning of antiderivative, which is f of x plus c. Okay, Now, how do we read this? We read this as the indefinite integral of f of x. That's how this is read. Indefinite, that is indefinite integral of x. That is how this is read. The integral symbol looks like this, and again it blew up that. This would be the integral symbol. And we'll actually talk about this later on as well. But the notation for the integral that you're looking at, the symbolism, if you will, the notation for integration, this notation was developed by Leibniz, okay, in the late 17th century. Okay. Now, as far as the components of this is known, the function f, it's called the integrand. Okay, so here in this notation, f is called the integrand. So for example, if I have sine x there, the integrand is sine x. Okay, and the differential of x, dx here, what's the role dx plays? At this point, the way we want to know this is that dx here is just a reminder to us that the integration is performed with respect to independent variable x. That's all that means. Okay, so that's what this is. That means we are integrating the function with respect to x. Okay, and remember, capital F of x is an antiderivative of little f of x. And of course, c is the constant here, and this is known as the constant of integration. Okay, and for all indefinite integral, we will have that constant. Remember, because there's a family of antiderivatives, so we have to have the constants with the constant here. Without it, the expression is not complete. Okay, so there you have it. So what I can do then, using this notation, the example that I made up, remember I have x to the 4 minus 7 was antiderivative of 4x cubed, right? So I can say the antiderivative of 4x cubed with respect to dx in this case is going to be x to the 4th, right? X to the 4th, that was this right in here. And because we're looking at the family of antiderivatives, right, we're going to use c here, c. So I'm not going to put minus 7. I'm just going to say it's x to the 4 plus c. That would cover all of them. Remember, this is what g of x is, and we're looking for g of x. Okay, so there you go. That's what we have. Now, next we're going to look at some basic rules of integrations. And we're going to look at these basic rules in light of the derivative. So we're going to look at the differentiation formula first, and then we take the reverse course from differentiation to integration. That is, we go through the antiderivative in order to do this. And here we are. So these are the basic integration formulas that are in your textbook and most calculus textbooks. Now let's actually we're going to go from left to right here. We're going to go in that direction, okay? Remember, we mentioned that the derivative of a constant is 0, right? The derivative of a constant is 0. So if we want to go back from 0 to the constant, we go through integration. So what we're saying is that this whole notation together means antiderivative. So the antiderivative of 0, if you will, is constant c, right? We don't need to say the antiderivative of 0 dx. You only cite the integrand. There you go. So we're looking at the antiderivative of 0, antiderivative of x to the n, cosine, sine x, and so on. Remember, dx it just tells us we're that's just the variable Okay, that's the variable that integration is performed with respect to. And because we only have a single variable here, so that's pretty self-explanatory. But for example, let's say I have, I don't know, w for weight times x dx, something like that. So although x and w look like variables, but because the variable of integration is dx here, is x, because I see dx, then we actually treat w as a constant. So w is no different than 100, although it looks like a variable, but it's not treated as a variable. So that's what dx, the role dx plays. Look at this one. Remember the derivative, the power rule of derivatives. The derivative of x to the n is nx to the n minus 1. Well, the antiderivative turns out to be that, and you can actually justify this. Let's see. Remember the derivative of x to the n, we bring the power in front, n times x to the n minus 1, right? So, to put more words into our action, so we're going to multiply x to the n by n and then subtract 1 from the exponent, right? Now think about undoing what we just did. To undo this, because I subtracted 1 from the exponent, right? To undo, I need to add 1 to the exponent, right? N minus 1, so I need to add 1 to the exponent. True? And because we multiplied in front by n in order to find the antiderivative, I need to actually divide. This is what it looks like at this point. I'm undoing my action again, right? So because I subtracted 1, I'm adding 1. And because before that I multiply by n, I need to divide by n. And you can see you get back what you started with. So that's what this part of the antiderivative is telling us to do. It just tells us that because you multiplied by n, we need to divide by, in this case, n plus 1, and because we subtracted 1 from n, we need to add 1 to the exponent. Okay? And you can see when you take the derivative, let's take the derivative of x to the n plus 1 over n plus 1. If you take that derivative, well, n plus 1 is a constant in the denominator, so that's just 1 over n plus 1. And derivative of x to the n plus 1 is what I want to find, and that's going to be, again, we bring n plus 1 in front, subtract 1 from the exponent, you get n, right? It's n plus 1 minus 1. So this will just give you x to the n. See how that works? And you get back to what you actually started with, right? So this is what we get, 2. Now, the derivative of sine is cosine in number 3. So antiderivative of cosine must be sine. Derivative of cosine is negative sine. Antiderivative of negative sine should be cosine of negative sine. So in other words, this is how I write it. The antiderivative of negative sine dx is cosine x plus constant. Now notice they have negative here, but no negative in the integrand. That's because you can multiply negative both sides, and there you go. This becomes positive, negative goes on the cosine. Okay, and the reason again for that is because we would like to keep our integrands as in their positive form, not with negative coefficients. The derivative of tangent is secant squared, so antiderivative of secant squared is going to be tan. That's what that is. Remember, and every one of these has a constant of integration attached to it. The derivative of secant is secant tan, so antiderivative of secant tan is going to be secant, and so on. Okay, now this chart, table, whatever you want to call it, we need to memorize this. Okay, and again, I'm not a proponent of memorization, but really at this point that's what we got to do. However, let me tell you this, some people actually have this memorized. Okay, they have it memorized. It's a lot easier because you already have these formulas memorized, right? So anytime you want to find the antiderivative, just remember, take the return path. So if you go from tan to secant squared, there you go. So you want to know what is the antiderivative of secant squared? Well, think about what was the derivative, the function whose derivative gave you secant squared. So a lot of people remember this in terms of differentiation formulas, and they just expanded or extended to the integration. And there you have it. So again, these are the antiderivatives that we're going to be working with in this section. Next, we're going to look at some of the rules of integration. Okay, so the rules of integration that will follow. So we have a couple of them. The rules of integration, they're pretty easy to remember, in fact. So the first rule of integration reads that if you have a constant multiple, the integrand is a constant multiple of a function, then we can actually bring the constant outside of the integral symbol. Okay, and you just find the antiderivative of f of x in this case. Okay, so that's that we are allowed to do. Now, the next rule is the addition subtraction rule of antiderivatives or integration. And the way this is remembered is that the integral of a sum or difference is going to be sum difference of the integrals. Okay, so the integral of sum of the integrals. The integral of difference or antiderivative of the difference is going to be difference of antiderivatives. And there you go. And that's all there is really in this section. So now we're going to look at a bunch of exercises. Okay, so here are the exercises portion of it for now. We'll look at more later when we're done with these that are in this section. And all of these, the first 30 exercises, the question reads, find the indefinite integral and check your answer by differentiation. Okay, so, and again, the reason it's called indefinite because we don't have a unique antiderivative. So it's not a definite antiderivative that we find. Because of that plus c, the constant, we have a whole family, infinitely many antiderivatives. So in that sense, it's indefinite. There is not a definite answer to this, to each of these. So we got multiple answers, in other words. But they're all of those answers are separated by a constant. So that doesn't mean you and I are going to get different answers for a given exercise. It's just all of our underlying functions will be the same, but all of the functions are simply separated by a constant. Okay, so let's begin with exercise number 4. In exercise number 4, we have the integral. The integrand is x cubed negative 2x squared plus x plus 1 and then dx. Remember, dx means the variable of integration is x. That's all we want at this point. And I know you're probably thinking dx as differential of x, which what it is. That was a small distance away from x. We'll talk about that kind of stuff later on. But for now, that's all that means. That means the variable of integration is x. Now, in order to do this, rule number 2 of integration, we had said or read that the integral of some difference would be some difference of integrals. So I'm just going to write this one time, only this time like this. In the future, I will avoid writing it this way. So that means I can write this as the integral of x cubed dx minus the integral of 2x squared dx, okay, plus the integral of x dx plus the integral of 1 dx. You see that? This is what we mean by some difference of, by integral of some difference is going to be some difference of integrals. That's what that means. Now, for each of these, I need to find the antiderivative. And all of these for polynomial function, let me recall the integral of x to the n dx is going to be x to the n plus 1 over n plus 1 plus a constant. That's what we're going to use for all of the polynomial functions, okay? Or functions that we can write it in the form of x to a power. So in the first instance, the first integral, n is 3. So in here, n is 3. That means I'm going to have x to 3 plus 1, that's 4, divided by 4. And let me write this. I'm just going to write plus a constant of integration, right? Because that's indefinite. So that would be the family of antiderivatives. I'm going to go minus. Next, I'm going to use rule 1 of integration. Bring the 2 out and take the integral of x squared. So n is now 2. The rule says this becomes n plus 1, 3 divided by n plus 1. Plus, and again, a family of antiderivatives means you have a constant out of this integral. Next, the derivative, or I'm sorry, the integral of x, and that is like, x means x to the first power, right? So n is 1. And you can add 1 divided by the sum, so it's going to be add 1, that's x2 divided by the x1 and 2, plus, of course, you get the constant of integration here, and then you have plus the integral of 1 dx, right? The interval of 1 dx, that's just going to be x, right? Let me go back here, and in this case, the integral of 1 dx is going to be x plus a constant, okay? Because you can think of like 1 as x to 0, right? There, and that's going to be x to the 1 over 1 plus a constant, okay? Now, the power rule, of course, works for derivatives here, but one thing you got to be careful, by the way, is when you find the antiderivative of x to the n, if n is -1, then this formula will not work. Okay, and here's why. When I have x to -1 dx, if I apply this formula, and I'm going to say that's going to be x to -1 plus 1 over -1 plus 1 plus a constant. That makes it x to 0 over 0. Division by 0, problematic, right? Undefined. So this rule, the power rule of integrals, does not work when n equal -1. Now, so how do I do that? Well, if I have the integral of x to -1 dx, which translates into 1 over x dx, how do we do this? Well, we're going to wait for this when we talk about transcendental functions. Then we'll talk about this one. Okay, so just want to put that on there. The integral of 1 dx, therefore, is going to be x plus a constant. So this is going to be x plus, and the constant of its integration is c4, right? Now, let me kind of tidy up this expression. Try, in other words, simplify it. So first one is going to be 1/4 x cubed plus, I'm going to actually be minus. I know the constant c1 is there, but I'm going to ignore it for now. I'm just writing the variables. Okay, and this was x4. Then it is 2/3 x cubed, and then plus 1/2 x squared plus x plus. Now, I have several constants right here. I have c4, c3, c2, and c1. Now, whatever these constants are, 5, 10, 15, 20, I can add those constants, couldn't I? Indeed, we could. So instead of 5, 10, 15, 20, and I'm just purely making up these numbers, instead of doing plus 5, plus 10, plus 15, plus 20, couldn't I write plus 50, which is the sum of these? So that same idea applies here. I'm just going to call this capital C. Now, capital C here is just the sum of all these individual constants. So, if you will, what I have is what we call a global constant that contains all of these individual constants that stem from individual antiderivatives. And there you go. We are done with that exercise number 4. Okay. Now the question says check by taking the derivative of this to make sure it works. We get the answer. I'm just going to do a cursory check here. The derivative of 1/4 x to the 4th, that's going to be 4x cubed. Of 2/3 x cubed, that's going to be 3x squared. Of 1/2 x squared, that's going to be half times 2x. Derivative of x is 1, derivative of a constant 0. So this is going to be x cubed negative 2x squared plus x plus 1. X cubed negative 2x squared plus x plus 1, and that's exactly what the integrand is. See that? So I checked it in this one, but the future ones I'm not going to check them. Just to save some time here, so the video won't be too lengthy. Let's take a look at number 12 next. In exercise number 12. Number 12, we want the integral of x squared plus 1 over x squared. Integral of x squared plus 1 over x squared dx. Now remember, when it comes to algebraic expressions, we only have one formula, if you will. We only have one integration formula, and that's it. So all of these expressions involving just the variable x, not the trig functions, but polynomial functions and so on, or powers of x, we need to somehow get it in the form that's amenable to the formula here, that we can work it with that formula. So what do I need to do here? Well, I'm going to actually divide individually by the denominator x squared. So x squared by x squared, that's 1 plus, let me do this, dx plus 1 over x squared dx. See? So I did two things. I split it into two integrals, and I divided individually by the monomial in the denominator. Now, of course, the integral of 1 dx, that's just x. And remember, I'm going to hold off on the constant here. Or if you want, there you go, plus a constant. And let me just rewrite 1 over x squared. Isn't that x to negative 2 using negative exponent rule? This will enable me to write it using this form, so I can apply the power rule to it. So the integral of x to negative 2 is going to be x to negative 2 plus 1, makes it negative 1, divided by negative 1, plus its constant, right, c2. Now I can combine these two into one expression. The answer is going to be x, right, negative 1 over x plus a global constant. The c is the sum of c1 and c2. That's what that is. Okay, and there we have that one. That was number 12. And here's the answer to number 12. Next, we're going to take a look at number 16. In number 16, we have the integral of pi squared plus pi plus 1 dx. Pi squared plus pi plus 1 dx. Now, remember, dx tells us the variable of integration, which is x. And we don't have x here. And pi is not a variable, right? Pi is about 3.14, right? The irrational number. So this is just a constant, isn't it? So in spirit, this is in the form of the integral of a constant c dx, which we had in the beginning. Oops, sorry. And there it is. The integral of a constant, just dx. I don't have it here. I have a special case where it's just 0. Okay. So that integral is going to be, you can bring the constant outside, right? And write it as 1 dx. So in other words, this is what I'm going to do. I'm going to bring the constant out to the front. That was rule 1 of integration. Here's a constant, right? That's a constant. Constant. That's what that is. Now, I can write it as a constant multiple of just dx, which is 1 dx, right? 1 dx, and the integral of 1 dx is just x, so it's going to be pi squared plus pi plus 1 x plus a constant of integration, and that's what that is. All right, and there we have the answer to this integration problem. So that's pretty easy. Again, the key is to recognize that what we have indeed here is a constant. That's the key. Next, we're going to look at exercise number 20. In exercise number 20, we get into trig functions. Now, with integrands involving trig functions, due to the identities, trig identities, it is possible to get different answers that look different, but we can work them to become the same. Okay? That's just in general. I'm not saying all of them turn out that way, but some of them turn out that way. So let's do number 20. In number 20, we have the integral of cosecant cotan minus 3 secant squared. And these were the trig integrals that we have, right? We have integral of cosecant cotan, that's what is in here. And then we also have secant squared. See, both of those are in our table of antiderivatives. Integral of secant squared is tan x, because derivative of tan is secant squared. And the integral of cosecant cotan is negative cosecant. One thing to note here, by the way, for all of the integrals involving functions, the answer to the integration problem is negative. Look at cosine. The integral of, right here. The answers, if the answer involves cofunctions, they're going to be negative, all of them. Okay, so with that in mind, let's actually do exercise number 20 now. In number 20, the integrand was the integral of cosecant theta cotangent theta negative 3 secant squared theta. And again, those functions, those two functions, are directly in the table. The integral of cosecant cotan is going to be negative cosecant theta, right? And minus 3 is a constant multiple that can be brought outside, so it's going to be 3. And of course, what I mean is that not outside of this integrand, because cosecant doesn't have 3 here, or I could have factored it. But when you write it as two separate integrands, it's going to be negative 3. There you go. It's outside of secant. That's what I mean. So it's going to be negative 3. And the integral of secant squared is going to be what? Tan theta. Okay? Plus a constant. And there we have that one. Simple, huh? These are quick problems. We can work them quickly. Let's take a look at the next one we're going to look at is number 24. The integral of sine 2x over cosine x, sine of the double angle. Number 24. Sine 2x divided by simply cosine x dx. And remember, in our table of antiderivatives, we only have the basic functions. We don't have double angles or powers of these functions. So anytime that happens, we got to think about how can I rewrite the integrand. Well, the identity for sine 2x, we all know that is 2 sine x cosine x, right? That's the only hope we have for this one, divided by cos x dx. And then we can, of course, divide the cosine out, bring the 2 in front, and that's just the integral of sine x dx. Now this is something that's in our table of integral or antiderivative. The integral of sine is going to be negative cosine x. And don't forget the c. These are indefinite integrals, means we want the family of antiderivatives. I have a couple of star ones here. 27, there's a hint, use this identity instead of 1. So that means in the numerator, actually. In the numerator, instead of 1, right in here. Use that expression. And then try sine squared by this, cosine squared by the denominator, simplify and see what happens. Number 29, we need to rewrite, for this one, because it's 1 minus sine. So one thing I cannot do is I cannot divide individually by when there's two terms. So for this one, let's see, I would try multiply top bottom by 1 plus sine x by conjugate of the denominator, and then go with that. Because what this will do, the denominator, you get cosine squared, right? And that's a monomial. Then you can pursue that. Okay, number 28 is one where we have to rewrite it. So in number 28, the integral of tan squared, hence rewrite the integrand. And number 30 is kind of like that one, except it's cotan. So for both of those, we need to use identities. Number 28, the integral of tan squared x dx. Again, we do not have that in our table of integral or antiderivatives. Now we do have the identity, right, for tan squared is secant squared minus 1 dx. And this would be the integral of secant squared, which is tan x, that's in our table. And the integral negative, the integral of just dx, which is 1 dx, that's just going to be a constant, right, plus c1, because we took that integral. We found that antiderivatives. So it's going to be now tan x minus x plus a constant. The constant that comes out of that integral, that integration process, would be c2, but then you combine c1 and c2 into a c. Okay, that's why. Now, in this step, if I leave out c1, this is incorrect. Why? Because I don't have a constant of integration. See, when I evaluated this should be indefinite, means that I have to have a constant. I called it c1, coming from the integral of secant squared. And there's your number 28. And number 30, we're done with 28. In number 30, we have the integral of cotan squared x dx. And now for this one, we can write it again just like we did for tan squared. We write this as cosecant squared minus 1 dx. The integral of cosecant squared is negative. Cotan, remember all the cos will be negative. The integrals that involve cotan, co-functions are all negative. So it's going to be negative cotan. The integral of negative dx, that's just going to be x, right? Negative x plus constant of integration. Okay, and there we have it. Now we can verify just to do this last one. Okay, if I take the derivative of the answer, I should get the integrand, right? This. So let me just say check derivative of negative cotan x minus x plus c. That's what we're doing. Now, derivative of some difference would be some difference of derivatives. Derivative of cotan x, right? Derivative of cotan x is going to be negative cosecant squared x. And derivative of negative x is going to be negative 1. Derivative of a constant is 0. Now double negative here on cosecant makes that cosecant squared x. Negative 1, right? And that's what that is, plus 0. And using the identity, cosecant squared x minus 1 is indeed cotan squared x. And that is exactly what this is. So it checks. Again, I just checked this one. Ordinarily, we don't check the answer unless we really, like maybe if the integrand is complicated and I'm not sure what I did was right, then we can always check it this way. All right, so we're done with that segment, and let's take a look at another segment. Okay, so here is the next segment of the exercises in this segment, the question reads, find f by solving the initial value problem. Now, what do we mean by initial value problem? So what we have in all of these, notice every one of these equations involve one form of derivative, be it first or second derivative. See, they all have equations involving derivatives. So what we call these equations, we call these differential equations. And that's all a differential equation is. It's an equation involving derivatives. Could be first order, second order, or higher order derivatives. Okay. Now, in a differential equation, we have initial value problems. Those set out or lay out the conditions that the antiderivative must satisfy. And what happens is we have, if you look at this, in every one of these, we have this added segment to the end of every problem here now. What this information will do for us is, instead of having a general form of antiderivative where there's a family of solutions, this actually narrows it down to a very specific solution, okay, rather than a family of antiderivatives. So let's take a look at, for starters, let's begin with exercise number 38. Okay, in number 38, we have f prime of x is equal to 1 plus 1 over x squared, and f at 1 is equal to 2. Okay, and then we'll look at the ones that follow. Now, before we actually have to do this, we have to start this, we need to start by finding the antiderivative. Okay, we need to find f of x. That's what we need to do. So f of x, by definition of antiderivative, is going to be the integral of f prime x dx, right? Okay. So in other words, antiderivative of this function is what the original function is going to be. All right. Now, to find this integral, that means I have to find the integral of 1 plus 1 over x squared dx. True? Now, to find this integral, I'm going to write it as integral of 1 dx plus the integral of x to negative 2 dx. Now, the integral of 1 dx, that's just going to be x. And the integral of x to negative 2 using the plus, x to negative 2, remember how that goes, negative 2 plus 1 over negative 2 plus 1 in the denominator. So that makes it x to negative 1 over negative 1 plus a constant. Okay, now, so I'm going to call at this point, therefore, our f of x is going to be x minus 1 over x plus a constant. So this is the general antiderivative at this point. Now, we have initial value problem conditions. There we go. So that we want f at 1 to be 2. F at 1 has to be 2. See, what the first part does is gives you a whole bunch that will satisfy this integral. But only one of them meets this initial value condition, the condition that f at 1 would be 2. Only one of infinitely many will satisfy that condition. So here's what we need to do. We need to plug in at 1, so I'm going to put 1 for x. That's 1 minus 1 over 1 plus a constant. But that should equal to 2, right? So we set it equal to 2. And then we solve for c. Now 1 minus 1, that's 0. From this we get c is equal to 2. So for these conditions where f at 1 has to be 2, then a very special, only a very specific antiderivative works. So the answer to this problem is going to be x minus 1 over x plus 2. There's only one antiderivative that meets the requirement of our initial value problem. Okay, or simply meets the requirement of set by initial values. There is number 38. Let's take a look at number 40 now. In number 40, this one, we have secant squared t plus 2 cosine t, and we want the requirement, the condition if you will, that f at pi over 4, 45-degree angle, must be root 2. F at pi over 4 must be root 2. So the derivative, the differential equation, is secant squared t plus 2 cosine t. Okay, let's do that one. In number 40, we have f prime of t is secant squared t plus 2 cosine t, and our initial value again was f at pi over 4 had to be square root of 2. Okay, so let's find f of t. To find f of t, we need to find the antiderivative of secant squared plus 2 cosine t dt. And remember, the integral of sum is sum of the integrals. So first we have to evaluate the integral of secant squared. That's going to be tangent plus twice. The integral of cosine is going to be sine plus a constant. Again, at this point, we have a family of antiderivatives. This is all possible functions whose derivative would be f prime t as given by the exercise. Now, the initial value kicks in. Okay, so for f at pi over 4 now, we're doing that. F at pi over 4, meaning that's tangent of pi over 4 plus 2 sine of pi over 4 plus a constant must equal to square root of 2. Now, tangent of 45 degrees or pi over 4 is 1 plus 2. Sine of pi over 4 is 1 over root 2 or root 2 over 2 once you rationalize it, plus a constant equal root 2. And from this, the 2's cross out, so I get 1 plus root 2 plus c equal root 2. Then you can subtract square root of 2 from both sides. This becomes 0, right? And this means c must be negative 1. Move 1 to the other side, becomes negative 1. Okay, and once we have c equal negative 1, therefore, the only antiderivative that meets the initial value condition is tan t plus 2 sine t minus 1. That's the one that works. There you have it. Number 40. In number 44 and 46, we have now second derivatives. So we need to find the antiderivatives twice, right? And therefore, in order to go from f double prime to f, I need to go through f prime. I need to be given 2 initial value conditions, right? One for f prime, the other one is for f. Okay. So for this one, f at 1 is 1, f prime, and it's got to be the same point. You see, at 4, at 4, at pi over 2, at pi over 2. It's at the same point. You can't switch those. So f at for number 44, f at 1 is 1, but f prime at 1 is 1/2. F at 1 is 1, but f prime at 1 is 1/2. And in number 44, we were given f double prime, right? Let me go that again. F double prime x is 1 over x cubed. 1 over x cubed, which we can write it as x to negative 3. So we can use the power rule of the integrals. F prime x, first derivative, is going to be the integral of the second derivative. In other words, the antiderivative of f double prime is f prime with respect to x. That means I have to integrate x to negative 3 dx, and using the power rule, that's going to be x to negative 3 plus 1 over negative 3 plus 1 plus a constant. And that makes it negative 1/2 x negative 2 plus a constant. Okay, now let's work our initial value problem here right away. So f prime at 1 means negative 2 times 1 to negative 2 plus a constant should be 1. That's what we're told. Now 1 to any power is 1, so that means negative 1/2 plus c equals 1. Add 1/2 to both sides and c becomes 3/2. Therefore f prime of x is going to be negative 1/2 x to negative 2 plus 3/2. True? So that's what we have in number 44. So that's our first constant. Okay. Now, let's see, just to make sure I copy the initial value right again. We have f prime at 1 in number 44. F prime at 1 had to be 1/2. And I plugged in, there you go, f prime at 1, so I plugged in 1 here. Oh, it's supposed to be a half. I put 1. Sorry. It's supposed to be a 1/2. F prime at 1 is a half, so that's a half. So add 1/2 to both sides, so c is 1. Sorry, now it looks better. I said it, I didn't write it correctly. Okay, and there we have it. So that is our f prime x. That is the first derivative function that meets those initial value conditions. Now, f of x is going to be the antiderivative of f prime x dx. And that means the integral of negative 1/2 x to negative 2 plus 1 dx. That's going to be negative 1/2 constant multiple. The integral of x to negative 2, again, negative 2 plus 1 is negative 1. Divide by negative 1. The integral of 1 dx, that's just x, and then plus a constant. Correct? And that's what this one is. Therefore, f of x is going to be negative, pi negative is positive. It's going to be 1 over 2x plus x plus a constant. Now, again, we have a family of antiderivatives. True. And what we need to do now is we need to work the initial value problems. Okay. Now, let's see. So what do we need to do? We need to, the initial value problem, we were given the initial value. F at 1 has to be 1. This time I'm going to make it equal 1. So f at 1 is 1 over 2 times 1 plus a constant. This should be 1, right? We're told that. So now I have a half plus 1, that is 3/2. Subtract 3/2 from both sides. So c becomes negative 1/2, looks like. And the solution to this exercise is f of x equals 1 over 2x plus x negative 1/2. And again, you can check by taking first, second derivative of this function, and you see that we will start with f double prime. We will have that, and we have also met these conditions. Okay, and that was number 44. Let's take a look at one last one in this segment. Is that 46? F double prime t is 2 sine t plus 3 cosine t, and the initial value f at pi over 2 1, f prime at pi over 2 is 2. Okay, f at pi over 2 is 1, f prime at pi over 2 equals 2. And in number 46, we are given f prime, oh, we're given second derivative or first? No. Okay, yeah, second, f double prime t, right? F double prime t is 2 sine t. F double prime t is 2 sine t plus 3 cosine t. Now, f prime of t is going to be the integral of 2 sine t plus 3 cosine t dt. That's 2 times the integral of sine turns out to be what, negative cosine, because derivative of negative cosine is sine, and the integral of cosine is going to be sine, because derivative of sine is cosine, plus a constant. Okay, f prime of t is therefore 3 sine t negative 2 cosine t. I swapped these two, okay, because of negative in front of cosine, plus a constant. Now, we put in the initial value conditions, right? At f prime at pi over 2 is 2. So f prime at pi over 2 is going to be 3 sine of pi over 2 negative 2 cosine pi over 2 plus a constant that should equal to 2. Okay. And let's see, sine of 90 degrees is 1, so that's 3 times 1. Cosine of 90, cosine is 0. Plus a constant equal 2. 3 minus 2 times 0, of course, is 0. Subtract 3 from both sides, we get c equals negative 1. Therefore, the derivative function f prime t is 3 sine t negative 2 cosine t minus 1. Now we need to find the antiderivative of this, which is f of t. It's antiderivative of f prime t. So that means I need to find the antiderivative of 3 sine t negative 2 cosine t minus 1 dt. Notice, by the way, the variable of integration here is t. That's why we have dt. Okay, so don't put dx, whatever the variable is. And the integral becomes the integral of 3 sine t. That's going to be negative 3 cosine t, because the derivative of cosine is negative sine, so we need a negative in front to offset. And minus the integral of cosine is sine, because the derivative of sine is cosine. So integral of cosine, antiderivative of cosine would be sine. And the integral of negative 1 dt, that's just negative t, and we're going to go plus a constant of integration. And then our initial value conditions were f at pi over 2 is going to be 1. F at pi over 2 is negative 3 cosine pi over 2 minus 2 sine of pi over 2 minus pi over 2 plus a constant, and that should be 1. Correct? And what else we do now? Let's see, let's evaluate it. Again, cosine of 90 degrees, that's 0. Sine is 1 minus pi over 2 plus c is 1. So I'm going to send these constants to the other side. So c would be 1 plus 2 plus pi over 2. The whole thing would be 3 plus pi over 2. Okay, 3 plus pi over 2, and we're done. F of t will equal to negative 2 sine t minus 3 cosine t minus t plus the constant of integration 3 plus pi over 2. And that's going to be the form of the function. Okay, and there we have it. So with that, we are done with this lecture and with this first section of integration. Okay, and that's all.